Okay. Yasuhiro Iwamura from Tohoku Universities. Okay, I will present recent experimental new results about the surface temperature distribution measurement. Okay. Okay, so. Okay. Basically, method of experimental method is the same Professor Kasagi's presentation. So briefly, I introduce. We use two nanostructured copper-nickel multilayer thin film with nickel bulk, two seeds, and nickel-based nanoscale multilayer thin film was preloaded hydrogen gas and heated rapidly to move hydrogen and induce anomalous large heat generation that cannot be explained by any known chemical reactions. Okay. Okay. Oops. Sorry. Okay, just a moment. Okay, so our experimental method so far, we measure the temperature in the center of ceramic heater by some couple, and also we measure the surface temperature by radiation thermometer, 2 thermometers. But experimental method so far is just a measurement area around center is about 2.5 millimeters, small, around the center. And this is the data taken by the heat burst data by the experimental method so far. So you can see red line means some couple in the center of the ceramic heater, and green and blue means surface temperature, A and B. And if we use nickel only, we can get this data. And this is the input power. We decrease about for 3 minutes, slightly decrease and return to the original value. And then TC and surface temperature return to original value. It's very natural. But however, if we use copper-nickel multilayer, you can see if we make a perturbation input power, we measure the heat burst like this. At this point, heat burst occur, and at this point, heat burst phenomena occur, and their energy propagated to the center of the ceramic heater like this. Okay, this is the data by original sulfur experiment. Okay, okay, and to understand this heat burst phenomena, we now assume the trapping hydrogen hypothesis. But it's just an assumption, but maybe hydrogen trapped at the tropic site. For example, vacancy and dislocation and void and something like that. Okay. So this is a new experimental setup for measurement of surface temperature distribution. Oh, this one is a surface temperature distribution measurement system. We introduced 2 systems, okay? And this is a figure, photos of experimental setup. This is a chamber, reaction chamber. And we have this sample holder in the center of the chamber. And this figure shows a front view of a sample, surface A and surface B. So we now measure a whole surface for two sample, yes. Okay. Okay, I will show you the recent experimental results. Okay, this is start. Sorry, just a moment. I'll start the slide. This is a, sorry, just a moment. It is a movie, but it does not start. Yes, so maybe.
Maybe if it's here, no?
Maybe we should change the.
You know.
Change the. Yes. Okay. Thank you.
Okay.
Thank you very much. This is a movie for the heat burst phenomena, surface temperature distribution during heat burst phenomena. At the beginning, it's a steady state. And this one is 700 degrees centigrade, blue, and white is 800 degrees centigrade. And in the center of the sample, or a little bit higher temperature like this. And this one is an old one, and maybe we can see the heat burst phenomena by the new, like this. We can see the heat burst phenomena like this. So it clearly demonstrated the heat burst phenomena by the surface distribution measurement. Okay. Oh. And next one is a measurement of a surface temperature distribution during a steady state excess heat. In this case, excess power is not so high. And this one is a 600 degrees centigrade. Lower temperature is 600, and higher temperature is 900 degrees centigrade. And you can see this temperature distribution looks like nearly uniform. And these are the raw data for the surface temperature distribution. One pixel is 18.7 micrometer and 17.7 micrometer. So as you can see, we see in this case a nearly uniform temperature distribution, and the average temperature is about 668, like this. However, in this case, this one is produce more higher excess heat. In this case, a non-uniform temperature distribution on the surface. Temperature scale is the same before, this one, 600 degrees to 900 degrees. But the surface distribution is quite different. And we can find some hot spot nearly more than 800 degrees, like this. And if we look at this hot spot, these are the raw data. A hot spot region, we can see the very high temperature here. And low temperature region is about over 600 degrees centigrade. So very high temperature gradient exists. And then if we consider only one-dimensional heat conduction, heat flux is about 100 megawatt per square meter. For example, first wall of the hot fusion reactor usually 2 megawatt per square meter. So this heat flux is enormously very large, very high. So, and then I will show you the transient behavior of these hot spots. So I present the analysis of temperature variation with time after heater power is turned off. these are the steady state hotspot. And this one is a steady state hotspot, and heater power off, I will show you. Okay. So we choose a 3 hotspot like this. So I will show you first one, hotspot number 1. This is the data hotspot 1. We can see this yellow area correspond to the hotspot. Very difficult to see the number, but these are the higher temperature region, and these are normal temperature region. And this graph, in this graph, temperature at each pixel are plotted in each point, in each pixels, along with the horizontal axis. Okay, and this is the time, and this is the heater temperature. And at this point, at 30 seconds, we switch it off, the heater. So during this period, no input power. And during here, steady state energy. As you can see, we can see that very large temperature gradient like this, like before, as I shown. And after switch it off, temperature gradually decrease like this. Okay? And apart from this hotspot region, this data is temperature change, time evolution of temperature in each point along this horizontal axis. Okay? In this case, we cannot see not so large temperature gradient, and temperature decrease gradually like this. It's a very natural, reasonable data. But around the hotspot are a little bit anomalous. Okay? And if we look at the hotspot 2, in this case, we have hotspots here exceeding 800 degrees here. And if we look at the temperature change for each pixel plotted along the horizontal axis here. And similarly, we can see the large, about 200 degrees temperature gradient exists along this axis like this. And after heater switch it off, most of the temperature decrease gradually, but some points are a little bit different way. And apart from the hotspot region here, we plot the temperature change for each point as along the horizontal axis. You can see a very small temperature gradient and normal decrease like this. However, this hotspot is different. In this case, we can see the very hot spot exceeding 1,000, because 1,000 degrees centigrade. It's an overrange for the measurement. And these data, these graphs are plotted, each point time change plotted along the horizontal axis. As you can see, these 2 points overrange, and after heater switched off, gradually decrease. And the other point here like this. However, if we look at these lines, this is the data for these lines. At this point, heater switched off, and initially temperature decreased like this. However, some points, some pixels, temperatures drop, and once drop, but then rise like this. It's very curious and anomalous. And these 3 points rise. However, these 3 points decrease. If we consider this phenomena occurred induced by the hotspot heat diffusion, it cannot be explained because these points and these points are same distance from the hotspot region. So it's a very difficult to understand phenomena. And also, we analyzed this line, vertical axis we plotted. And these 2 are very hot spots above 1,000 degrees centigrade. And if we look at this along this vertical line, we can see in the steady state heat release time, very large temperature gradient exists, about 400 degrees here, you can see. And this spot also is above heater temperature. And at this time, heater switched off, and some pixels are once reduced and rise like this, a very strange manner. And apart from the hotspot region, we also see the very strange data here. This graph shows the temperature distance along the vertical axis. When the steady state energy generation here, a little bit large temperature gradient exists. But just after heat off, the temperature gradually. However, at the 150 second, these 3 points rise again like this. And moreover, 381, this point is nearest from the hotspot, but not so high, and this region is highest. And also, in this case, these spots gradually decrease, temperature for decrease. So it's very complicated, and at present, we cannot say definite conclusion, but anyway, these data shows that there is no doubt that hotspot exists during heat generation. But what is responsible for the transient behavior around the hotspots, as I shown, after the heat turned off? Some results appear to be explainable by summer diffusion. So hotspot heat diffuse towards around. But summer diffusion alone is difficult to explain, as I shown this data and this data. Yes. So we can now, it is possible, I think, in my opinion, it is possible that the heater was turned off and high concentration of hydrogen trapped in the hotspot. So if we assume that this area, hydrogen concentration very high, and so produce a very high excess heat, if we consider. And then these high concentration hydrogen diffused out and causing the temperature to rise at the new location. New location, for example, here and here. New location where it is more likely to cause a reaction. But anyway, at present, we can't draw any definite conclusions at this point. Thank you. And finding out what is happening is an important issue to be addressed in the future. And more important, it is also important to clarify what kind of physical, chemical properties make an area of hotspot. Why hotspot generated? Okay, I would like to conclude. Two-color surface temperature measurement system was introduced to measure the surface temperature distribution during anomalous heat generation and heat burst. The experimental method is to generate anomalous heat by hydrogen-absorbed nanostructured copper-nickel composite and rapid heating in a vacuum. And second, measurement of surface temperature distribution during a heat burst phenomenon, specifically observing how temperature rises on the surface, have improved the credibility, reliability of the existence of heat burst phenomena compared to conventional experimental method. And the existence of hotspots with very high temperatures has been clearly demonstrated. And then observation of the time evolution behavior around the hotspot after the heat are off have yielded some suggestive data. This is the acknowledgement. This work is mainly supported by the Thermal Electric Energy Technology Foundation. Thank you for your attention.
Thank you, Dr. Iwamura-san.
Thank you very much
Questions? Go ahead.
for Professor Iwamura for this presentation. I have a bad question.
Yeah.
You said you use two-color surface temperature measurements. So is it sufficient to be sure all these measurements are not an artifact of emissivity?
Yeah.
This is very important.
Emissivity, of course, change. But if we use a two-color method, usually it depends, it's okay. So under the assumption, gray body radiation, as Professor Kasagi says. So usually two-color measurement is correct for the measurement.
Okay, I have a question.
Yeah.
Did you do any, it seems to me that it's the flux of hydrogen in your system.
Yeah.
Now, did you do experiments pumping the hydrogen instead of being always under hydrogen?
Usually we use only hydrogen.
But did you try under vacuum? When you pump out the hydrogen, maybe you should see something also.
Pardon?
During the time you're pumping,
Yes.
because there'll be a flow of hydrogen out of the
Yes.
layers, you should see hotspots also, maybe.
Maybe.
I don't know. You have to try.
Maybe. I did not measure.
Because we have seen excess heat more when we are pumping than we have when we are
Good.
stable.
I imagined. I think so. I agree with you.
Thank you, Dr. Iwamura.
Yeah.
Thermal changes affect many parameters. Have you considered the arrangement that you showed on the slide as either a magnetic fluid or a phase conjugation in standing wave nodes? And in that context, as the temperature changes, the thermal resonance phase conjugated nodes in the metal shift, changing the location of the active areas. So like you've actually got standing waves sitting there in your disk, and they are setting up phase conjugation. And then as the temperature drops, those nodes, because the vibration mode in the metal is changing. Just phonons, yes.
It's interesting.
Yeah.
Thank you. Thank you. Thank you for your comment.
Okay.
Conrad? Conrad?
Yeah. So my question is,
Yeah.
have you tried to estimate how much energy will be produced in one hotspot.
Yeah.
The area is, I understood, about the size is about 20, 30 micrometers.
Yeah.
So if you have a
Yeah.
lattice constants and everything, you can calculate how many hydrogen atoms should contribute and how much energy you will produce.
Yeah. Very, very simple one. Not so complicated. Just one-dimensional, and if we consider the penetration depth like 10 micron, because surface temperature measurement, not the temperature, whole sample, just only surface area. We can estimate, in that case, about 0.1 watt from hot spot to lower region. So, but just it's a one-dimensional conduction only. Actually, radiation from the surface to the wall. So, anyway, it's very large, I think. Okay.
Yes, sir.
So for these systems, wherein these systems have been preloaded with hydrogen,
Yes.
is there temperature program desorption data? At what temperatures do you see desorption peaks?
Desorption and absorption data? Yeah,
For
we
temperature.
have,
At
but
what temperature?
here we do not have. But always we are taking. Yes.
What is the temperature typically?
Usually we absorb about 250 to 300 degrees.
And desorption is? Desorption, yeah.
During the desorption process, we mainly 700 degrees or 600 degrees.
Okay.
Okay.
Okay, thanks.
Mathieu?
Yes.
Yeah.
Thank you for your
Yeah, thank
presentation. Have you studied the surface crystallographic features? Maybe
Yeah.
with a EBSD mapping,
Yeah.
you can obtain something and
Yeah.
you can correlate the hotspots to the crystal structure.
Right. We are now trying to make hotspots region, but at present it is difficult to say.
Yeah, I look forward.
Yeah, we are looking for and seeking intensively. Right.
Francesco?
Okay, very simple.
Yeah.
Again, the composition nickel copper.
Yeah.
In your
Yeah.
case.
In this case, we changed copper nickel. This one is about the copper. Nickel by copper is 5, around 5.3 or something like that.
5 to 1.
Yeah, 5 to
1.
1. Nickel 5 and copper is 1.
Okay.
And yes, these data mainly.
Okay, okay. Thank you.
All right, let's carry on with the next.
Okay, thank you. Thank you very much.
Thank you so much.